Which way is this wave moving? Is something moving across the screen? Or only up and down? Then what is moving across the screen? Here too, dots are moving up and down. Why isn't the effect the same? There must be something special about the way these dots move to produce a wave which itself seems to move. In this program, we shall be asking a lot of questions. And here are two important questions about waves. I want you to keep them in mind and see if you can discover the answers to them during the program. First, in a wave, does anything move along? And how can dots moving in straight lines produce a wave? When you see a large question mark like this appear on the screen, it means the question is particularly important, and we shall repeat it at the end of the program for you to take down. But why we should be studying waves at all is probably the first question you want to ask. I'm sure you've heard of sound waves and radio waves, and perhaps even of light waves. The fact is that waves are a very important part of our daily lives. Indeed, the fact that I'm able to talk to you now depends on two different kinds of wave. But first, let's look at some wave motions which we can see clearly. These have great practical importance. For example, in the design and testing of ships. An exact model is made and is placed in a large tank of water to observe its behavior, often using slow-motion film. This large vibrator at the end of the tank generates waves of the kind that the real ship will meet at sea. The models can be attached to a travelling gantry which runs down the length of the tank. The reactions of a model to real conditions can be carefully recorded using a mass of instruments on the gantry. But in the school laboratory, it's easier to start with a single wave. We can do this very well on a slinky spring. I expect many of you have seen one. It consists of a coil of sprung steel, and of course all the turns are connected together. If I give this end a sudden flick, we can see a single wave travel down the slinky. A single disturbance like this is called a pulse. So this is a pulse wave. Clearly the pulse travels quickly from one end to the other. But what happens to each individual coil? Here it is in slow motion. Notice the reflected wave. Here's another apparatus where we have even more control over the waves. It consists of trolleys connected together with springs. In the slinky we have coils all joined together, and in this apparatus we have trolleys joined together. If I move the first trolley across, the springs pull the second trolley across to one side as well. But it doesn't move at once because it always takes a little while to get anything moving. When it does move, the next springs pull the third trolley across, and so on down the line. And I can move the first trolley back. Now watch a complete pulse wave and its reflection. And again. The speed with which a wave travels along this apparatus depends on how the apparatus is made. In fact, depends on the medium through which the wave travels. And we can sometimes find out quite a lot about the medium by knowing how fast the wave travels. How do you think I could alter this apparatus so that the wave went at a different speed? Well, one thing I could do would be to put weights on each trolley. Do you think that would make the wave go faster or slower? Have a guess. Have you decided yet? Well, here's another line of trolleys, just like the first, only each one has a heavy lead block on it. Watch. Well, the wave goes more slowly, it seems. Just for comparison, I'll send a pulse down the second line of trolleys at the same time as I send one down the first. You ready? Yes, it's slower on the trolleys with lead blocks. More weight, less speed. Perhaps some of you thought of having more springs. What difference do you think that would make? Well, here we've got a third line of trolleys, and these are all connected up with twice as many springs as the first line. Watch. It looks as if the wave is going faster now. Just so you can compare it with the original line, again, I'll send the pulse wave down both together. You ready? Yes, well, with this extra force, the wave goes faster. More force, more speed. To summarize, here's the pulse at normal speed. More weights on the trolleys make the wave slower. And more force between the trolleys makes the wave go faster. Now here's a problem for you. I should like you to consider after the broadcast how we could make a wave on this machine travel faster or slower by altering the machine in some ways. Notice how it's constructed. The dots are at the end of cross arms, and these are all fastened to a central wire which gets twisted back and forth. The important thing is that once again, like the slinky and the trolleys, all the parts are connected together. Our machine is rather elaborate, but you can easily make a simple one for yourselves by taking a rubber band, gluing drinking straws to it, and fastening drawing pins in the ends. So I want you to think of two ways of making a pulse wave go faster and two ways of making a pulse wave go slower. Remember the trolley experiment and how this apparatus is made when thinking about your answer. I'll remind you about these questions again at the end of the program so that you can jot them down then. We've been talking a good deal about the speed of waves, so how fast do you suppose the waves go on our machine? To find out, what two measurements do you need? Yes? Time and distance. The machine is 2 meters long from here to here, and we shall measure the time it takes the wave to travel from end to end by using this electric clock. An electrical contact at one end starts the clock. The small hand goes round once a second, and the large hand moves on one division every second. And the second contact at this end stops the clock. Right, we'll reset it. Ready? There. It took nearly 2 seconds. 2 meters in 2 seconds. So the wave must be travelling about 1 meter a second. And I can't change that speed without altering the machine in some way. Natural water waves are rather more complicated than those on our wave machine. But those from the bow of a boat are fairly regular and smooth. Do you think their speed is always the same? Notice that the rowing boat moves up and down like the dots on our wave machine. Most important, you probably noticed that water waves are usually continuous. To get continuous waves on our machine, we should need to keep the end moving up and down like this. A motor is more convenient, so we'll attach one to the machine by this bar and set it going to produce vibrations. This is how we produce the pattern that you saw at the beginning of the program. The pattern shows a continuous wave. You may think we've changed the speed which the waves move along the machine now, but we haven't. What have we changed then? Yes, the rate at which the end is vibrating, the frequency of the vibration. We now have about 1 complete vibration per second, and a complete vibration is called a cycle. The frequency is 1 cycle per second. And if we speed the motor up, we can increase the frequency, say, to 3 cycles per second. Now, I told you that the speed of the wave along the machine didn't change. I wonder if you believed me. And I told you, too, that the frequency had changed. But something else had changed, too. Do you know what? Well, watch. Try to choose one particular wave and follow it along the machine. And now it's going at a higher frequency. Is the wave travelling any faster or slower? It looks about the same to me. Well, how do we explain this? Here's a diagram of the 2 waves moving side by side. Let's halt them and look at the lower wave. This, you probably know, we call the wavelength, the distance from a point on one wave to the corresponding point on the next wave. Let's say it's 10 centimeters. Now watch the wave in progress, and notice how many crests pass this point in 1 second. Let's suppose that it's 3 in 1 second. This then is the frequency. Can we now calculate the speed of the wave? If each wave is 10 centimeters long, and in 1 second 3 waves have passed, then the wave has travelled 10 times 3, or 30 centimeters, in 1 second. In fact, the speed is the wavelength times the frequency. How does this fit with our knowledge that the other wave travels at the same speed? Notice that the frequency is a third of what it was. 1 cycle per second for every 3 of the lower wave. But the wavelength is 3 times what it was, 30 centimeters instead of 10 centimeters. But we get the same speed, 30 centimeters per second, when we multiply the 2 together. This then is an interesting connection between speed, wavelength and frequency. We tried to confirm this result on an actual moving wave on our machine. And to do so, we used this slow motion film. In a moment, you're going to see in this film the machine start from rest, and after 1 second, we're going to freeze the film and look at the picture we've got. Remember, the small hand on this clock goes round once in a second. Ready? Watch the small hand on the clock as well as the wave. There, it went round once. We're seeing what happened in 1 second. Here is that last picture. Now, first, wavelength. One wave is about 50 centimeters long. That's half a meter. And now at frequency, in 1 second, we have 1, 2 cycles. So the frequency is 2 cycles per second. Here is the information. Wavelength, half a meter. Frequency, 2 cycles per second. Can you calculate the speed? Yes, 1 meter per second. Here it is in the picture. 1 meter in 1 second. That agrees with the speed we measured earlier on the wave machine. So we get the same speed, 1 meter per second, both for a continuous wave and for a pulse wave. This then gives us a general formula connecting speed, wavelength, and frequency. If you don't know the symbols for these three quantities, you should find them out for yourselves. Remember that this formula applies to any sort of wave. We shall be concerned with much faster ones. Vibrations too fast to see with the naked eye, and so you can't tell if there's a wave pattern or not. This is the case with this vibrating string. One simple way of seeing what is happening is to use a stroboscope. Here is what the vibrating string looks like through a stroboscope. Another wave pattern, so we shouldn't be defeated by faster waves. But now for this week's question. I'll remind you what they are so that you can write them down. First, when a wave travels, does anything move along? And connected with that, how can dots moving in straight lines produce a wave? Second, on the wave machine, I want you to think of two ways of making the wave go faster and two ways of making them go slower. Well, that's all for today. Just now, and earlier in the program, I asked you if anything moved along with the wave, and I haven't been very helpful in answering that question. But if you were sending continuous waves down this machine, I think you'd find that you needed a certain amount of energy to do it. What happens to this energy? Well, look at the other end of the machine. We've got here a small ratchet device, and this is making a wave go up. This weight is raised by the ratchet. Now can you answer that question?